Okay, good evening, everyone. This evening, Team Markov will be discussing with you Chapter 14, Markov Analysis. The discussion this evening will be centered around the following outline that has been presented, which includes a brief history of A.A. Markov. What is Markov Analysis? When can Markov Analysis be applied? How is Markov Analysis applied? The advantages and disadvantages of Markov Analysis. We'll also present examples of Markov Analysis. We'll perform demonstration of Markov Analysis in Excel QM spreadsheets by screenshot tutorial as well as demos. We'll review an overview of additional readings related to Markov Analysis. Additionally, our discussion will focus on the 6 learning objectives for Chapter 14, which are as stated. We'll recognize state of systems and their associated probabilities, compute long-term or steady state conditions by using only the matrix of transition probabilities, understanding the use of absorbing state analysis in predicting future states or conditions. We'll put Markov analysis into practice for the operation of machines. Additionally, we'll recognize equilibrium conditions and steady state probabilities and understand the use of absorbing state and fundamental matrix. We'll also share multiple real-world examples from different industries as it relates to the Markov analysis when applying the models process to either tools, that being Excel spreadsheet or by way of Excel DM by demonstration. We will begin the discussion this evening with a brief history regarding the mathematician Andrei Andreevich Markov. Andrei Andreevich Markov was a Russian mathematician who is known for his work in number theory, analysis, and probability theory. He extended the weak law of large numbers and the central limit theorem to certain sequences of dependent random variables, forming special classes of what are now known as Markov chains. For illustrative purposes, Markov applied his chain to the distribution of vowels and consonants in Pushkin, who is a Russian poet as well, in the poem Eugen Onegin. At present, much more important application of Markov chains has been discovered. Markov was in his 50s when he did his work on Markov chains. In the photograph that we've presented here, it was taken in 1918. Markov was 62. Markov's life spanned from 1856 to 1922, and he passed at the age of 66 years. Some notable aspects and moments of Markov include the probability and poetry were unlikely partners in the creation of the computation tool. At various times in history, one could assume that the probability and poetry were unlikely partners in the creation of a computational tool. However, over 100 years ago, the Russian mathematician Markov founded a new branch of probability theory by applying mathematics to poetry. Delving into the text of Alexander Pushkin's novel in the verse Eugen Onegin, Markov spent hours sifting through patterns of vowels and consonants. On January the 23rd, 1913, he summarized his findings, however, in an address to the Imperial Academy of Sciences in St. Petersburg, Russia. His analysis did not alter the understanding or appreciation of Pushkin's poem, but the technique he developed, now known as Markov chain, extended the theory of probability in a new direction. Markov's methodology went beyond the coin flipping and dice rolling situations where each event is independent of all others to chains of linked events, where what happens next on the current state of the systems. Additional notable aspects and moments of Markov include the following. In his early years, Markov showed outstanding talents for mathematics, but performed rather poorly in other subjects. He wrote his first mathematic paper while in secondary school. However, it was not until Markov was in his 50s before he performed his work in Markov chains. It was clear that mathematics was the right subject for Markov to study at the university. And in 1874, he entered the physics and mathematics faculty at St. Petersburg University. Markov graduated in 1878, having won the gold medal for submitting the best essay for the prize topic set by the faculty in that year on the integration of differential equations by the means of continued fractions. He now wished to train to become a university professor and work for his master's degree over the next 2 years. He was awarded his degree in 1880 for his thesis on the binary quadratic forms with positive determinant. This thesis was outstanding, and the work was regarded as very, very highly esteemed by very notable statisticians. It represents one of the finest achievements of St. Petersburg School of Number Theory, and perhaps even of all Russian mathematicians. After submitting his master's thesis, Markov began to teach at St. Petersburg University as a private dante, which is a private lecturer, while working for his doctorate. He was awarded his doctorate in 1884 for his dissertation on certain applications of continued fractions. Markov became an extraordinary professor at St. Petersburg University in 1886. He formally retired in 1905, but continued to teach for most of his life. One notable other item that I think we should share here is, as I noted here on this slide, it's over Markov's lifespan, he published more than 120 scientific papers on number theory. And as you can see, it expanded to continuous fractions theory, differential equations, probability theory, and statistics. Also, Markov's classical textbook, Calculus of Probabilities, was published 4 times in Russian and translated into German. From 1906 on, Markov published his first works on time-dependent random variables. Markov's early work was mainly in number theory and analytics, algebraic continued fractions, limited integrals, approximation of theory, and the convergence of series. After 1900s, Markov applied the method of continued fractions pioneered by his teacher, Pufneti Chokovich, to probability theory. He also studied sequences of mutuality-dependent variables in hopes to establish the limiting laws of probability in their most general form. He proved the central theorem under fairly general assumptions. Markov is particularly remembered for his study of Markov chains, which is a sequence of random variables in which the future variable is determined by the present variable, but it is independent of the way in which the present state arose from its predecessors. This work founded a completely new branch of probability theory and launched the theory of stochastic processes. In 1923, Norbert Wiener, an American mathematician, became the first to treat rigorously to continuous Markov processes. The foundation of general theory was provided during the 1930s by Andrei Kolmogorov, which is a Soviet mathematician. It is worth once again pointing out, however, that although Markov developed this theory of Markov chains as a purely mathematical work without considering physical applications, he did apply the idea to chains of 2 states, namely vowels and consonants, as referenced earlier. In literary text, His interest in poetry was not, therefore, an entirely separate interest from his mathematical work. We'll transition now to discuss what is Markov analysis. The Markov chain is a special case of the stochastic process. Recently, the methods have been used to estimate the matrix of transitive form from the observing state of the system. It is a random process where all information about the future is contained in the present state. In addition, the main components in developing the Markov chain model are state transition matrix and probability, both of which will summarize all the essential parameters of a dynamic change. To clarify the interrelationships of the model, the Markov chain is one of the prominent tools that has been developed to solve complex real-world problems such as prediction of a state of circumstances. The following is a simple equation that depicts the results in probability of the future event for decision making. As you can see from the illustration here, P, which is considered the next period, equals P, which is current period times transition probability as noted as P. The assumption of the Markov model. The following are the assumptions of a Markov model. The probability of moving from a state to all other sums to 1. The probabilities apply to all systems participants. The probabilities are consistent over time, and the states are independent over time. For example, you have a set of states, as shown here, S equals S1, S2, S3, etc., and so on. The process starts at one of these processes and moves successfully from one state to the other. If the system is currently, for example, at Si, then it moves to the state Sj at the next step with a probability by, as referenced, Pij. And this probability does not depend on which state the system was before the current state. So the following illustration is a visual representation of the intricacies that I just referenced when analyzing the assumptions within the Markov model. To highlight the structure of the proposed Markov chain method, the framework is visualized here in Figure 1. The Markov technique is adopted in this discussion and further examples. The proposed method is a stochastic process by introducing the simplest way of statistical dependence. In addition, the future behavior of this process is not concerned with the past behavior as previously discussed. To highlight the structure of the proposed Markov chain method, the framework again is visualized in Figure 1. The algorithm of the proposed Markov chain method consists of 5 steps, which is shown as follows. Step 1, define the state for the Markov chain process. Step 2, construct the state transition matrix N and state transition probability P. Step 3, configuration of the ergodic Markov chain. Step 4, Markov process probability values. And step 5, forecasting and model validation. Additionally, we'd like to share with you some common terminology that is associated with the Markov analysis. You can be expected to either in your study or application to recognize or to utilize this terminology as it relates to Markov models and processes. As you've heard me share the terminology stochastic processes, it deals with the collection of a random variable indexed by some set that you can study the dynamic of the system. Independent events. One of the best ways to understand with this example of flipping a coin, since every time you flip a coin, it has no memory of what happened last. The sequence of head and tail are not interrelated. Hence, they are independent events. Dependent events, which is considered two events said to be dependent if the outcome first event affects the outcome of another event. Random variables, a variable whose value depends on the outcome of a random experiment or phenomenon. Steady state probabilities. As you continue the Markov process, you will find the probability of the system being in a particular state after a large number of periods is independent of the beginning state of the system. The probabilities that you find after several transitions are known as steady state probabilities. Now we'll discuss when can we apply the Markov analysis. So in shifting our discussion towards the Markov analysis being applied, we have to consider, like all qualitative methods in reliability engineering, Markov analysis requires component failures to be assumed for non-repairable systems, and in addition, repair rates for repairable systems. Markov analysis uses these rates within a mathematical model that includes all of the possible states of a system. Within this model, the failure and repair rate then represents the rates at which the system makes transitions from one system state to another. Failure and repair rates therefore become transition rates within the model, which is called a Markov chain. The chain is in fact more accurately described as a network of interconnected states. Interconnections being present between two states in the network if a transition, for example, component failure or repair, leads from one of the states to the other. So for example, in any given small interval, a system that is in one specific state X at the start of the time interval will move to some other state if a component of the system fails during the time interval, or a component that was already failed in state X is repaired and returned to service, for example, during the time interval. Fundamentally, what Markov analysis does is to look at the network of all possible states of a system, which is called the state space of system, where transition rates between these states are determined by the failure and repair rates of the components. The simplest model or network assumes that components can be in just one of two possible states, failed or working. And a system within components can therefore be in any of the two second possible states. The simplest network therefore constrains two states between two transitions take place according to the failure and repair rates of the relevant components. An example state space diagram for two component systems is shown to your right. There is one further assumption within the model of which Markov analysis depends. This assumption is that the transition rates between the state of a system do not depend on the states that the system has been in. Usually it is assumed, however, that the transition rates are constant and do not change over time. This means that the time for any given transition to take place has an exponential distribution. The unique feature of an exponential distribution is that it is considered memoryless, in the sense that a given transition does not become more or less likely as time passes. As a consequence of this constraint transition rate feature, the feature of a Markov system depends purely on its current state and not the historical transitions by which it has reached its current state. It is this feature that gives the memoryless characteristic of Markov systems. Mathematically, this characteristic provides huge benefits in terms of simplifying the analysis of a system and enables its precise reliability or availability to be calculated. this particular application when the effects of small design changes need to be qualified or when design changes for high integrity systems are investigated. Okay. Now we'll move further to discuss how Markov analysis can be applied. The following is a very high-level walkthrough of an example of Markov analysis being applied in a grocery store scenario. This walkthrough is being shown in a step-through process through Excel from a visual perspective of the application. It certainly can appear very lengthy or rather cumbersome in comparison to what the remainder of our team will share with you as outlined when demoing the Excel QM option associated with Markov analysis. So for the following example, let's analyze the market share and customer loyalty for Murphy's Food Liner and Ashley Supermarket grocery store. Our primary focus is to check the sequence of shopping trips of a customer. You can assume the customer can make one shopping trip per week to either Murphy's Food Line or Ashley Supermarket, but not both. Using the terminologies of Markov processes, you refer to the weekly periods or shopping trips as the trials of this process. In each trial, the customer can shop at either Murphy's Food Liner or Ashley Supermarket. The particular store chosen the particular store chosen in a given week is known as the state of the system, in that each week, because the customer has two options or states for shopping in each trial. With a finite number of states, you can identify the states as follows. State 1, the customer shops at Murphy's Food Liner. State 2, the customer shops at Ashley Supermarket. The given transitioning probabilities are as follows. We've demonstrated the applications here for state 1 and state 2 on the right. You can see here were the current weekly shopping periods and equivalent to the state of conditions for both Murphy's Food Liner and Ashley Supermarket. Similarly, you can have the relevant information that is applicable for customers who shop lastly at the supermarket. This is what this is demonstrating here. It's allowing you to see the comparisons for both Murphy's Food Liner and Ashley Supermarket. If you're looking at this from a computation perspective that has already gone through the application, for example, through a Markov analysis through Excel QM. Hereafter, the probability of Murphy's after 2 weeks can be calculated by multiplying the current state probabilities matrix with the transition probabilities matrix to get the probabilities for the next state. That's a lot of words, but if we look at the generalized formula to illustrate what I just spoke of, it allows you to see the representation here that relates to the equation that we just referenced, which is what allowed for the computation of the previous illustrations of the model. Okay. If we were to perform the Markov analysis in a spreadsheet, this is where I was referencing it can become very cumbersome, but we're going to walk through this process for those that may not utilize Excel QM, for example. So let's solve the same problem using Microsoft Excel. So again, I've noted the steps by words here for us. So step 1, let's say at the beginning, some customers did shopping from Murphy's and some from Ashley's. This can be represented by the identity matrix because the customers who are at Murphy's can be at Ashley's at the same time and vice versa. Throughout this walkthrough, you will see these steps illustrated in several visual representations of an Excel spreadsheet. Step 2. Let's also create a table for the transition probability matrix. You can see a demonstration of this to your far left. Step 3. Now you want the probabilities at both the store at first period. First, let's design a table where you want values to be calculated. And we've demonstrated this here in this representation. Step 4. Now let's calculate the state probabilities for future periods, beginning initially with Murphy's customers. Probabilities can be calculated using an Excel function. It's rather small here to see on the representation of the spreadsheet, but we do have this here to the far right for further review. To use this, first select both the cells in Murphy's customer table following week 1. After applying this formula, close the formula bracket and press Ctrl-Shift-Enter all together. Then you will see the values of probability. In step 5, as you have calculated the probabilities at state 1 for week 1, now similarly you'll calculate the state 2, excuse me. The only thing that will change that is current state probabilities for week 1's probabilities will be considered to calculate future state probabilities. In step 5, now all you have to simply do is copy the formula from week 1 cell at Murphy's and Ashley's and paste into the cell until you find to the period that you particularly want. Okay. As it is noted here, if you had started with 1,000 Murphy's customers, that is 1,000 customers who last shopped at Murphy's, our analysis indicates that during the 5th weekly shopping period, 723 would be customers of Murphy's and 277 would be customers of Ashley's. Moreover, during the 10th weekly shopping period, 676 would be customers of Murphy's and 324 would be customers of Ashley's. Similarly, now let's calculate the state of probabilities for future periods beginning initially with Murphy's customers, for example, for week 1. You can see here we're just taking and doing the same process here for Ashley's. We continue forward now for week 2 by just dragging the formula from week 2 to the period you want. Now let's calculate the state of probabilities for future periods beginning initially with a Murphy's customer. In the 5th shopping period, the probability that the customers will be shopping at Murphy's is 0.55. And the probability that a customer will be shopping at Ashley's is 0.44. In the 10th period, the probability that a customer will be shopping at Murphy's is 0.648. And the probability that a customer will be shopping at Ashley's is 0.352. All of these numbers that I've referenced obviously are depicted in the chart here in the Excel spreadsheet. And lastly, the following illustrates from a graphical perspective how the share is going down at Murphy's and increasing at Ashley's of customers who last shopped at Murphy's. So this representation, again, is in an Excel spreadsheet format. As you can tell, it's very cumbersome. It takes more steps, but it certainly can be done. And if a person were to take this process over Excel QM, obviously it just takes into account that there's more probability for errors, where the software would lead someone to have more flexibility to be able to thoroughly analyze and understand this, I think, more efficiently and quickly. So lastly, what we'd like to do is discuss with the folks here the advantages and disadvantages of the Markov analysis. There's a considerable number of items that are listed here, so we'll go through them. The advantages of the Markov model are a good way to model local, overlapping sets of information, which reflects cues to our understanding of regions. Additionally, Markov chains provides a stochastic model of diffusion that applies to individual particles, which give us the foundation for diffusion. This stochastic diffusion also provides a useful model of the spread of information through an image. Additional one key advantage of Markov models is that they lend themselves to dynamic programming solutions. A primary benefit of Markov is the simplicity and out-of-sample forecasting accuracy. It is better at making predictions than more complicated models. Markov analysis has the advantage of being an analytical method, which means that the reliability parameters for the systems are calculated in effect by a formula. This has the considerable advantage of speed and accuracy when producing results. Markov analysis gives a deep insight into the changes in the system over time. As you can see, there is a considerable amount of advantages over disadvantages that we've discovered. And just to share a few of the disadvantages, they include the following. Markov analysis is not very useful for explaining events, and it cannot be the true model of the underlying situation in most cases because it depends only on the present event and not the past event. Markov analysis requires great care during the model building phase, since model accuracy is all important in obtaining valid results. Markov analysis depends to a greater extent on the experience and the judgment of the modeler. However, taking both of these into consideration, both the advantages and disadvantages, nonetheless, as I've stated here, Markov proved that the independence of random variables was not a necessary condition for the validity of the weak law of large numbers and the central limit theorem. He introduced a new sequence of dependent variables called a chain, as well as a few basic concepts of chains such as transitional probabilities, irreducibility, and stationarity. His ideas were taken up and developed further by scientists around the world, and now the theory of Markov chains is one of the most powerful theories for analyzing various phenomena around the world. Okay, so in conclusion, after reviewing all the foundation and the intricacies of how Markov analysis was developed, a high-level overview of how it can be applied through Excel, we're now going to transition. At this time, Dustin Wilson, which is a part of our team Markov, will further our discussion into the actual application of Markov analysis and provide an example of the process in Excel QM. He'll also discuss further reading material for consideration.
Hi, everyone. This is Dustin Wilson. As many of you know, I have a career in healthcare, and I'm really excited to bring the healthcare perspective with Markov at the forefront. And I really wanted to give you something that is a realistic situation that could really happen, and something that really does happen in our facility. And I've noticed in studying Markov that it's not used in our facility, but it's going to be, because I'm going to implement it. It's actually very useful. And although this equipment example is healthcare based, overall, the theme is that, you know, these equipment issues and being able to predict whether equipment would be working, not working, et cetera, is important, and it really relates to a qualitative outcome. So I hope that none of you have ever seen the machine that's on the screen, and I hope that you never have to, but it is a radiation therapy machine. And so people that are getting radiation treatments for cancer, that's the machine that's used for that. Those courses of treatment vary, but it's very important that the people getting radiation therapy do not veer from their course of treatment, if at all possible. So, you know, just setting it up that if the machine is down, it could very much pose a problem. In addition to such equipment, you know, as the radiation therapy machine, it's called a linear accelerator. There are usually only one, maybe two, if it's a large facility. A lot of facilities locally don't have them. Smaller ones like Sycamore Shoals, Franklin Woods, they refer all their patients to their larger hospitals. So very complex equipment. And if it goes down, it's likely the only one in the hospital. So, you know, that poses a massive problem. All right, Kim, you can go to the next slide. So why is Markov important from a healthcare perspective? Well, it directly relates to patient care. If a machine is down, like I just said, it's a major issue. And basically what you can do, and I can tell you that executive leaders in healthcare love this, when you use quantitative variables and you use data and you use matrices and analysis to predict or show them what could or is going to happen. So basically you can use this Markov as a part, you know, you don't really want to use it as the only tool, but you can use it as a part of your report or your return on investment or your equipment packet to support, you know, upgrading the equipment, or to support that certain equipment might need to stay and we might need to upgrade a separate set of things. So, and then likely executive leadership is going to require some sort of information when they're making budgeting decisions. And, you know, I would definitely, if I were an executive leader, I would want this in there because it can really help, as I said, prioritize what needs to be replaced. Likely there are replacement cycles where you can see at a certain year when one is projected to be replaced, but sometimes certain things are pretty reliable and they might not need to be replaced, whereas something else might be having a lot of issues and you might need to change your attention to that. It's easy to implement in healthcare because in healthcare, you have to document everything all the time. So when the machine is down, if it's in our radiology department, if it's in our cardiology department, they are documenting that every day because any equipment in healthcare has to do quality assurance daily, sometimes multiple times a day. So you're going to have those records and you're going to be able to have those probabilities and percentages to use for this. And it's going to be pretty accurate. And then there are downstream effects related to healthcare equipment downtime. You know, there are many. I just really tried to pick a couple, but one of them, a big one, is wait times. If you have 500 patients scheduled for a procedure and the machine goes down, half of the time you have 250 patients that didn't get their treatment or exam, and you got 250 patients you either have to get to the community or you have to integrate them back in at another time, which is going to affect the patients already scheduled at that time. So it's a major issue from a continuity of care perspective. And again, you know, this is a healthcare perspective, but I think you can apply these qualitative issues in whatever industry you may be in or may be going to be in. Another one is employee morale. There are not many facilities that I've worked at that will pay people for doing nothing. So if the machine's down and it's projected to be a long fix, which sometimes those parts are rare and they have to be shipped in. So sometimes you're looking at days and they'll send you home and you won't get paid. And that's a morale booster big time for employees. All right, next slide. So let's go over a scenario, and a linear accelerator is also called a LINAC, so I shortened that here. But essentially, we're going to start with two states to consider. And state one is that the LINAC is working. State two is that it's not working and it's down. So this scenario down here basically is telling you that in the past 3 years, when they've evaluated this, that 95% of the time in the current month, it worked properly if it worked the previous month. And then, of course, everything has to equal 1. So 5% of that month, it wasn't working if it was working in the previous month. And then the next little paragraph is basically telling you that there is an 85% chance that it will function correctly this month if it was not functioning correctly last month. And then conversely, there's a 15% chance of it not functioning properly this month if it was not functioning properly last month. And this is a little bit of a different example than you're going to see in a lot of the textbooks and information if you research the equipment problems. On that second portion, you're going to see the percentages flip a lot more, and you're going to see like the 15% instead of the 85. But this is, again, I tried to make this realistic for you. And where it is cancer treatment and in healthcare, there is so much riding on these machines that they usually will get in pretty quick and do anything they can to fix it. So your percentages are not going to be flipped like you're going to see in some other things and some other machines. All right, Kim, next slide. So I think it's important that we write this out and show you, if you want to do this by hand, what this looks like. I think it's important on an aspect that even when you know how to do it in Excel, there are sometimes you want to maybe understand it a little bit further and get into the weeds and the detail. And then also it's good just to have a second check. If you question Excel and you're like, I'm not really sure what's going on here, if my computer's messed up, if that just doesn't seem right, then you've got a manual way to do it. So you're going to start at the top and you'll see the 1 and the 0. Those are your states. So state 1 is that it's working properly, and that's the 1. State 2 is the 0, and that's that it's not working properly. And then you're going to see your matrix of transition probabilities beside it, which is the scenario we went over, that 95%, 0.95, 95% of the time it's working at the current month if it was working in the previous, 5% that it wasn't working in the current month if it was not working, was working in the previous. And then there's the 85 and 15 that we went over as well. So basically, to come up with that future state of 1 month from now, you're going to take your states 1 and 0, and you're going to multiply them here. So you're going to take that state 1 and multiply it by 0.95, and then you're going to take state 0 and multiply it by 0.85. You're going to do the same thing on the right side of this equation. You're going to multiply your state 1 by 0.05, which is the probability of it not working if it worked in the previous month. And then you're going to take your state 2, which is 0, and you're going to multiply it by 0.15, which is the percentage that it is not working if it was not working in the previous month. So you end up with 0.95 and 0.05. That's 1 month from now, 95% chance it's going to be working, 5% chance it's not. And that makes sense to me because of the basis you have to use, you're really a thought process of the machine you're working on here. That is a realistic thing. All right, next slide, Kim. So, if we project it 1, 2 months out from now, and I even did 3 at the bottom just so you would see, you're going to do essentially the same thing to predict the next state over and over again. The only thing you're going to do different in the middle part where you see 2 months from now is instead of starting with 1 and 0, you're gonna start with the vector of state probabilities at the end, which is 1 month from now. So you're going to replace the 1 and 0 with 0.95 and 0.05. And then you're going to do that exact same calculation. And you'll see in 2 months, we're still at 95% that it's going to be working, 5% it's not going to be working. And then just to show you 3 months, same thing, you're going to switch out that vector of state probabilities that you used for 2 months with the ending vector of state probabilities for 2 months. So you're going to take the the 0.95 and switch it for 0.945, and you're going to take the 0.05 and switch it for 0.055. Do that same equation, and then we can see at 3 months, it is starting to go down a little bit as far as the working percentage. It goes down to 94%, that it will be working, 6% that it won't be working. And again, knowing the history of these machines, that makes sense to me. So that is likely realistic. You know, it's good to use reason on these because you know, when you know that the machines are highly likely to mess up when they're brand new or when they're super old, then if this one is about a 15-year-old machine, then this makes complete sense to me. And this is something that you can use on all the machines in your facility and kind of as a comparison tool as well. All right, next, Kim. So now we're going to do it in Excel QM, that exact same scenario. You're going to go to the menu and click Markov, and then it's going to pop up this menu. I like to type in my title just because I like to label things, and then you're going to name your sheet. So the number of states are 2 states. You know, we started with not working and working. And then as far as the number of transitions, that's the number you want to predict forward. We're going to do 2 for this, but you could do as many as you'd like. So you click OK, and then it's going to pop up this. And then Kim, if you'll pause it right there so that I can talk about it a second. So it's going to pop this stuff up for you that you can enter. So it's going to be pre-populated. So the first thing that you want to do is enter your initial state. So you're going to enter, and you'll see this on the next slide, but I just want to talk it through. You're going to enter 1 under the initial state of state 1, and then a 0 on the initial state of state 2. And then as far as states 1 and then states 2, you're going to enter your matrix of transition probabilities that we came up with in that previous example. All right, Kim, you can go to the next slide. So this shows all that information entered. And you can see that we entered the 0.95 and the 0.05, the 0.85 and the 0.15. And what you end up with where it says end probability given, you'll see the 0.95 and the 0.05. We can cross-reference that to our manual calculation and know that in 1 month, it's 95% chance it'll be working, 5% chance it won't. And then you can see down there where it says 2-step transition matrix, that's saying 2 months from now. Again, you look at that end probability, and you're going to see 4.5% that it will be working, and then the 5.5% that it won't be working. And basically, you're going to enter that information, hit run Excel solver, and it's going to give you that steady state as well over there. All right, Kim, you can go to the next slide. So I want to give you a little bit of a different example that's also realistic. CT scanners are notorious for going down for extended periods of time. And so this is the same scenario as far as you've got 2 states, you're going to enter them, but instead of 2 transitions, we did 6 transitions because I want to know 6 months from now what I'm really looking at here. Am I looking at a potential issue or not? And so here you're looking at the probabilities being 85% that it's going to be working if it was working the previous month, 15% that it will not be working if it was working the previous month. And then that second state, that second line, you're going to see a 10% chance that it will be working if it was not working last month, and then a 90% chance that it won't be working if it was not working last month. And that is more realistic for a CT scanner. So you see that you end up at that first month projected that an 85% chance it will be working, 15% it won't. But then you can see that as we go down to the 6-step transition matrix, which is saying 6 months from now, you're looking at about a 51% chance it's going to be working, which gives you a 49% chance it's not going to be working. And that does project a problem. Again, you're not going to want to use this as the sole, information if you go to executive leadership or your supervisor or whoever in your organization to discuss the replacement or an issue with equipment, but it's definitely going to be a part of the story. All right, next slide. So final thoughts on, specifically the healthcare scenario. It's, we're using quantitative data to predict and really offset qualitative issues. And a couple things I listed there that are just massive, and they're not just in the healthcare industry, they're really in tons of industries now with social media, so many, the ease of reviews, for businesses and places and healthcare providers. Patient trust is massive, and patient satisfaction is massive. In healthcare, those scores are qualitative, but they do quantify those, and they do affect things, ratings of the hospital, reimbursements, so on and so forth. So for the, of course, issue that you don't want, you want patients to trust you. There are monetary problems there. There are reliability issues with the facility there. So those are really important. And then, of course, delayed care. That's a big one. You know, you lose a patient's trust one time, and you've got to really fight hard to get it back. If your machine goes down 3 times in a week, you got to fight really hard to get their trust back, because they worry that something will happen to them or it will not do the test properly. So those are major issues. And in healthcare, I can really see Markov playing a large role in the discussion of equipment. So much so, you see the second point, that I really think it really should be included in strategic planning. Most facilities engage in strategic planning and have a strategic planner. Most industries have those. And then, you know, most in facilities, there are different services: surgery service, medicine service. Most of those are going to have an annual service briefing where the service presents to executive leadership their projected plan for the year. And this would be a wonderful tool to use, so that everyone can be on the same page and really see the numbers and understand what could happen. It's a tool to hold the manufacturer accountable, and it's also a tool to use to decide if you want to do a service agreement, if you want to renew the service agreement, or if you even want to go with that brand again. And then it earns leadership trust, leadership's trust. It gives leadership the ability to trust that you know what you're doing when you're using something like a Markov analysis, that you have the education. And so I think it's really important that it be integrated in healthcare and really a lot of other industries. All right, next, Kim. So I just wanted to highlight another example. This could be in healthcare. This could be really in any industry, but this is more of an HR related model. So this was a part of the additional readings that we provided. And this one, basically, this research really aims at predicting social dysfunctions and how they affect organizational performance. So they did 3 models. The first model they did was on employee fluctuation. And essentially they used 2 factors: age and years of work experience. And then they built the vector based on things such as the number of resignations, terminations, and retirements. And then they wanted to project that for 6 months or 6 periods. All right, next, Kim. Models 2 and 3 focused on employee conflicts and absenteeism. And then, long story short, what they really found is that you can use this information to reduce costs to the facility or to the organization, and this one's the big one for me, is implement plans to basically overcome issues that somewhat haven't happened yet. You know, you can see them happening 6 months down the road. And so you might see an issue with absenteeism, or you might see an issue with employee conflicts, for instance. So that's the time when you use a Markov and you evaluate that. You might say, hey, let's get together as leadership now. Let's do a crucial conversations class with our supervisors, and let's head this off now. And let's not wait till 6 months down the road to see what happens. They highlighted the same things that we've already said so far. Markov's simple and easy to understand. And it's one of those things you can present to your executive leaders or to other people in your organization, and you can easily explain it without having to do an in-depth overview of it for them. They're basically only worried about the probabilities. So as long as you can explain that to them, that's what they're interested in. They did highlight that it's important to build a clear, valid matrix. That's with anything. You really want to get the best information that you can and the most accurate information that you can. I like to use it. I like the thought of using it as a simulation. So saying, hey, if this looked like this in 6 months, what would we look like? So I think it could be used as a proactive tool on that front. And then it really just just like we highlighted in healthcare, it really provides valuable information to executive leaders on the direction that they want to take their business and how to get there, and more importantly. So that's my information on healthcare. If you have any questions, please feel free to reach out to me. I could talk about healthcare all day and the issues around it and Markov in relation to it. So I think we're going to move to Yago next. Yago, are you there?
Yes. Hello, guys. Yago, thank you, Dustin. Now we're gonna talk about recognizing the state of systems and their associated probabilities. First, we have to define what are the states of a system, although the other people have talked about it previously, but the states of a system are used to identify all possible conditions of a process or system. A machine can be either working properly or not working properly, and these two possible outcomes are the two different states of the machine. In Markov analysis, we assume that the states are collectively exhaustive and mutually exclusive, which means that the list of states is finite, which has an end, and a system or process can only be in one state at a given point in time. Once the states have been identified, the next step is to find out their associated probabilities. Individually, the probability is known as the state probability, and collectively, these probabilities need to be placed into a vector of state probabilities and add up to 1. Below, you can see the mathematical representation of the number of states and the probability of being in state. Next, Kim, please. When dealing with only one system or process, it is easy to know in what state it is in a given point in time using the formula mentioned previously. But when we're dealing with multiple systems, we need to calculate the vector of state probabilities. As an example, I'm going to calculate the vector of state probabilities for the top US phone carriers. And imagine in your city there are only 3, Verizon, AT&T, and T-Mobile. Okay, we assume that there are 100,000 people purchasing a plan at any of these 3 companies in any given month, and the probability that a person will be buying a plan or a phone for any of these 3 companies is the following. State 1, Verizon, would be 30,000. Will be 30%, 0.3. State 2, AT&T, will be 40%, 0.4. And state 3, T-Mobile will be also 30%, 0.3. And placing the probabilities into the vector of state of probabilities, we get the following formula. Next, please, Kim. All right. So in this formula, in this vector, we have P1, which is the vector of state of probabilities for all 3 carriers for period 1. We have 0.3, which is probability that a person will shop at Verizon, which is state 1. We have 0.4, which is the probability that a person will shop at AT&T, which is state number 2. And we have 0.3, which is the probability that a person will shop at T-Mobile, which is state 3. We now know that the market share for these 3 companies for the first period, and once we know this, the following calculation should be the customer loyalty and the percentage of customers that come back the next month. By computing these numbers, we can get an idea of next month's market share for each carrier by multiplying the market share of each month by the percentage of customers that will come back next month. By adding this number to the percentage of customers that will leave T-Mobile and AT&T to come to Verizon, we obtain Verizon's market share for next month. And we can do the same thing for the other 2 companies to find out the next month or next period's market share. Next, Kim, please. All right, here we're gonna calculate the long-term or state conditions by using only the matrix of transition probabilities. Here we have the matrix of transition probabilities, which allows us to get from a current state to a future state. Following the example we've been using, we have 0.6, 0.2, 0.2, 0.1, 0.8, 0.1, and 0.2, 0.3, and 0.5. These are the rows of the matrix. And as you can see here, 0.6, 0.6 is the probability of being state 1 after being state 1 in the previous period, which means to stay in Verizon. So a customer comes into the, or consumes or purchases a plan in Verizon and decides next month to continue with the company. So that's the percentage. And then we have 0.2, which is the probability of being in state 2 after being in state 1. This means to change from Verizon to AT&T the next month or the next period. And then we have 0.2, which is the probability of being in state 3 after being in state 1, change from Verizon to T-Mobile. And then in the row 2 and 3 of the matrix, you can see the same for the other companies. Next scheme, please. One of the purposes of Markov analysis, I'm sorry, here. Yes. Once we have the matrix, I'm going to show you how to calculate long-term conditions, but by using this matrix, okay? As I was saying, one of the purposes of Markov analysis, as explained in previous slides, is to predict the future by looking at what happened in the past, okay? Continuing with the example we have been using of the US phone carriers. We are going to explain how to compute long-term conditions to find out about future market shares of these companies. If we assume the current period is 0, to calculate the next period, we assume that N1 is equal to N0 multiplied by P, which is the matrix. Or if we are in any period, we can compute the state of probabilities for period N+1 using this formula. Going back to finding about next period's market share, we need to calculate the vector multiplied by the matrix, and we obtain 0.28, 0.47, and 0.25. This is the next period market share for each of the 3 companies. Okay, Verizon market share will be 28%, AT&T market share will be 47%, and T-Mobile will be 25%. Furthermore, we can also calculate what the state probabilities will be in any time period in the future by changing the formula above for the following, where the state probabilities for n periods in the future can be obtained from the current state probabilities and the matrix of transition probabilities. And as you can see, the formula below. Yeah, that's fine. Change the slide, please. Now I'm going to show you a video of like Dustin did in his healthcare example. I've done the example I've been using to do the Excel QM. I put also the title for the Markov Analysis US phone carriers. I've used, yeah, the number of states 3, because there are 3 companies. And then I've obtained this, and then you need to plug in the numbers, as you're going to see in the following slides. Here you put the numbers of the matrix in state 1, state 2, and state 3, and you get the steady state conditions highlighted in yellow. You can see the results for the steady state. The steady state vector is a state vector that does not change from one time period to the next. In this example, in the steady state, we'll end up with 24% of the market share, AT&T with 55%, and T-Mobile with 20%. And that will be all for my part of the presentation. Now, I think Daniel is going to talk. He's going to continue with the presentation. Thank you.
Hey guys, it's Daniel. Can y'all hear me?
Yes, we can hear you.
All right, awesome. I didn't want to be presenting to the air. I was having a little bit of technical difficulties earlier, but I think I got it fixed. All right, so as we've been discussing, we've already gone through the history of Markov analysis and how useful it is in all kinds of different areas and industries. We've learned a lot of different things about the state of systems, various examples with that. And now we're going to be moving forward with another important part, which is understanding the use of absorbing state analysis in predicting future states or conditions. A basic understanding of absorbing states is very good here. When you're in any given state, you're essentially absorbed by it, and you will constantly continue to remain in that state regardless of what occurs in your analysis. Once you're in one state, you cannot simply move from one state to the other in the future, as this would affect your results in a manner that is not reputable or accurate. They can also be understood as various categories in which analyses are organized and performed. So essentially an absorbing state is a state that you enter into and you cannot be moved out of. The definition of a state, states are used to identify all possible conditions of a process or a system. A possibility can result in being absorbed into various states at one time, while still only being recognized as one essential possibility. We've got an example of this in future slides. It's really going to help with understanding that. Once a system is in an absorbing state, that probability of it being in an absorbing state at any point in the future is always going to be 100% because it's unchanging. On the other hand, the probability of going from an absorbing state to any other state is always going to be 0. Next slide, Clem. An easy way to understand this, the textbook gives a great example of this when it talks about the accounts receivable. There are going to be 4 primary states. It's like whenever you're paying debt, one absorbing state is going to be your bills are all paid. You don't have any more debt that you owe and you completely paid everything off. And the other absorbing state is essentially going to be your bad debt state, whereas you owe money in some form of increment, whether that be overdue more than 3 months, overdue less than 1 month, or overdue between 1 and 3 months. So you can see there's 2 absorbing states here that you can be absorbed into, but you're never going to be able to be in both at one time. You're never going to be able to be paid. Your debt's never going to be paid while you still owe, and you're never going to be able to owe if your debt is paid because you don't owe anything. By knowing this and the number of people and payments in any given state, we can also gain an understanding of the people and payments that are going to be in the future states due to this analysis as well, due to the fact that they are essentially unchanging and deemed to be absorbed. This is a very good example of understanding how absorbing states work and how they can be used to predict your future outcomes, because if you're not paying off your debt periodically, or if you're not paying it off at all, you're always going to be remaining in one state of debt. But if you've paid it off, it's gone and it's erased from your record, and you don't have to worry about it anymore, and you're always going to have your bills paid in that sense. Next slide, Kim. So there's a lot of industries that use machines, whether it be in production or in a factory setting, or like Dustin discussed earlier in healthcare settings. There's so many ways that Markov analysis can be used to analyze machines and how they operate. And in essence of the states of a machine, machines can either be functioning correctly, or they can be functioning incorrectly or not functioning correctly. They can be used in various settings and stages of production and labor. They can cut down on your labor force, and machines such as robots and the like are used in these settings, and they can make a drastic impact on how smoothly production is performed and how well it is done and how efficiently it is done as well. Next slide, Kim. So I work in the construction industry. I work for Fastenal, and I sell construction supplies and industrial supplies. So I'm around a lot of moving parts and machines, and I sell people the parts that they may need to fix it. And a good example of this, I think, is we do a lot of business with the Oshkosh Corporation. If any of you guys are familiar with it or unfamiliar with it, Oshkosh Corp is based out of Oshkosh, Wisconsin. And they specialize in the welding and assembly of military vehicles and trucks. So they provide trucks and cars for the transportation of our military, whether it's locally or overseas. They use a lot of robots of various shapes and sizes in order to effectively speed up production rates that allow room for accuracy and less manual laborers. So it affects their efficiency and various other things in production. The data gained from Markov analysis can be used in providing machine quality assurance as well as maintenance needs. And it can also measure the time at which the machine is inactive for whatever reason, whether that be the machine that is turned off or the machine is in need of maintenance or is acting in a manner that is not supposed to be. It also allows for more accuracy when it comes to making parts and doing it efficiently, rather than simply relying on the manpower or the laborers that they have who may be inexperienced or become tired during their shift. So the use of machines is very important in this industry, and being able to analyze them and their effectiveness and how well they work in certain situations is always going to be beneficial for the company and making it more profitable and efficient as a whole. Next slide. So in terms of absorbent states, in a sense, you could say that there are two absorbent states here. Either the robot is functional or it is not functional. And there are alternative states that go along that funnel into these, which it could be functioning but not correctly, whereas it's making parts at a slower rate, or it could be functioning not correctly through meeting the quota for the parts, but having error. So the way that these robots work is they can produce up to, I mean, it depends on what setting it's on. I mean, you can set it based on what production environment that you're in. But a typical welder can make around 10 to 12 parts a day. And that's working at max capacity and max effort, while these robots can make around 40 or 50 parts a day when they're fully operational and doing everything they're supposed to be doing flawlessly. So it's a big difference, and it's a very essential thing for these companies to use them and to understand when they're functional and when they're not functional. So we got some probabilities here, similar to what Dustin talked about earlier. We've got a 70% chance that the probability of the machines will function correctly this month, given that it was functioning correctly last month. And then we've got only a 30% chance probability that the machine will not be functioning correctly this month, given it was functioning correctly last month. And on the other end of the spectrum, we've got a 20% probability that the machine functions properly this month, given that it was not functioning properly last month. And then we've got an 80% probability that the machine does not function correctly this month, given that it was not functioning correctly last month. So there's a big gap in these. It almost sort of flip-flops into different results here. And each of these probabilities, it's important to know, must come out to equal 1. Next slide, Kim. As you can see, I've got a manual calculation here of this, and we start with the first month being the 1. So you multiply the 1 by the 70% and also by the 30%, and then you use 0 for the 80% and the 20%. And when you add all those together, your matrix points are going to be 70% and 30%. So the probability of the machines functioning correctly turns out to be 70% of the time based on this analysis, while the probability of it not functioning properly is around 30%. Now, if we want to calculate the next month, month number 2, we're simply going to be multiplying what we got for the first month and incorporating it into the problem here, as it says we're going to be multiplying the 70% by the 70% and adding it to the 30% times the 20%. And we're going to get 55 from that. And then we're going to multiply the 70% by the 30% and adding it to the 30% times the 80. We're going to get 45. So after the 2 months, the machines at Oshkosh will still be functioning properly at a 55% rate, and they will not be functioning properly at a rate of 45, which is alarmingly different from the first month. So you can see how important recognizing Markov analysis is in this situation, because of how drastic the numbers are and the percentage changes are, and figuring out how to make them more efficient and working in a timely basis. Next slide. I got some results that I'm going to review here. Though the percentages of effectiveness appear to get lower in regard to the months moving forward, Markov analysis can be beneficial to engineers or maintenance people who are determining possible changes that need to be made, whether that's cosmetic or internally, such as batteries, moving parts, different things that affect the machine in general. With these outcomes in mind, better analysis of what needs to be done in terms of machine maintenance, downtime, and effectiveness can be judged better and attacked from an angle that will be beneficial to cost savings for the company and how to program their robots in order to make the company more profitable in the long run. Markov analysis has shown in the case of military automotive production to show room for improvement in both their robots and the amount of manpower that they use in production, assembly, and welding components. Next slide. And as you can see, I couldn't get my QM Excel to record, but I essentially did the same thing that Dustin and Yago did when it came to going to the Excel QM and going to the Markov analysis. And you can see that we got the exact same results here as we got for the problem that we did. It's very important to know just how effective that this is in the usage of machines and how to make them more efficient in both business aspects and how to save money for the company in terms of maintenance and the amount of manpower that they use for their corporations in the long run. That's all I have for this, my portion of the presentation, but now I'm going to hand it over to Haley.
Can everybody hear me?
Yes, we can hear
Yep.
you.
Awesome. Okay, I will try not to keep everybody too long, but I am going to review over how to recognize the equilibrium and steady state probabilities and the absorbing states and fundamental matrix. And it's going to tie pretty much hand in hand with everything that's already been presented in this PowerPoint. So I'll just go ahead and get started. Typically, you want your market shares when trying to find your equilibrium between 0 and 1. Following that, there is a point on the market values and probabilities that is known as the equilibrium, and that is also known as steady state probabilities. They are both the exact same concept. An equilibrium will exist when the state probabilities find a consistency, which basically that means is that from now and into the future, each state will be verbatim and every number outcome should be the same, which would create your equilibrium. So when the equilibrium point is met, that means your state probabilities will be the same for this period and moving forward, and they should not change. The easiest way, you can compute this by hand, but I'm going to show you an example soon about how to compute this in Excel with the Excel QM that we downloaded. Next slide, Kim. So this was actually in the reading that is in chapter 14 in the book, and this is showing how you are able to compute the equilibrium. So just give you a second to look over it. Next slide, Kim. So moving into absorbing states and fundamental matrix. Up until this point, we have learned that you can have different future states or you can have the exact same future states, but there comes a point where you're going to get put into one state known as the absorbing state. And once you are put into a said state, you will stay in that state, quote unquote, being stuck in it. This is known as the absorbing state. At the bottom, you can see that there is a chart. It is paid bad debt less than 1 month and 1 to 3 months. This is basically showing where you stand in a debt. So this is typically used in accounting with accounts receivable, and that will be shown next. Next slide, Kim. Yeah. Back up one. Yeah, right there. Sorry. So this is just a clear view of the 4 states. The probability once you are in these states will be 1, which goes back to the equilibrium of being between 0 and 1. You'll be at a 1. So you can be put into either state. You don't have to, it's not that one is, you're going to bounce between them. If you are in state 1, that means you were paid and all your bills are good. If you're in 2, you have bad debt and you were overdue by roughly 3 months. If you're in 3, you're overdue by roughly a month. And if you're in 4, you're overdue between 1 and 3 months. And this is, like I said, when companies use this to check out debts, see where they are with their accounts, etc. Next slide. So this is the Markov example, which is pretty much the same as Daniel and Dustin's example. So when you go into Excel, you'll have the Excel QM tab open, and you will pull the drop-down menu to Markov chains. And I chose a problem out of the book to make it easier to read and go back and check out. So this is the opening table for that problem. Next slide. When you click on the drop-down menu and you click Markov Analysis, like Dustin showed, this will come up. And just like him, I do like to label things also. So for the number of transitions, which would be what you want to check out for the future, it could be if you want to check out something for 5 weeks or 5 days, you'll put that in transition. Next slide. And you can see how the number of transition is pulled up. So originally, you can see where my original table is put in, state 1 and state 2. And when you, when you want to find the equilibrium, you can look to the right. After you hit in top left, run Excel solver, this will pop up and you'll keep solver solution. And once you click OK, it'll help you figure it out. And in P1, it shows that that is your equilibrium in your steady state. You can see how it started at 0.75 and continued for the next 2. That would be your equilibrium. And at the bottom, I also added in the 3 questions that went along with the problem, just to clarify on the probability of the car starting, the probability of the car not starting, and if the matrix doesn't change, the probability that it will start in the future, 75% being your steady state. Next. Does anybody have any questions?